So in lecture 3, we talk about direction fields and solution curves. So we're going to use direction fields to draw solution curves of the first order differential equations. So unfortunately, the method that we use, this is the qualitative methods that we use here, is only for the first order differential equation. And if you want to visualize the solution curves for direction field and solution curve for the second order differential equation, you have to do something else. So I'm not going to do that for the time being. But I want to emphasize that direction field and solution curves that we cover in this lecture is just for the first order differential equation. Later on, we're going to identify equilibrium points or equilibria and indicate flow directions on a phase line. Again, what we're covering for the phase line is just the first order differential equation. So the rationale for this particular lecture notes is that in many cases, first order differential equations cannot be solved analytically. Or so far we cannot invent another analytical method solution to actually solve for the differential equation. However, we are still very lucky to to have other approaches, especially qualitative approaches. When you analyze the differential equations qualitatively, what you can learn is that you can study the behavior of solutions. You can learn about the directions that the solution is going to move in. Right. And also answer certain questions, right? How does the solution behave near a certain point? And how does the solution behave when the solution go to infinity, or when you take the limit of the solutions to infinity? So we talk about that, we talk about direction field solution curves, and then later on equilibrium point and phase line. So direction field, why do I give you this particular example here? Right, so it's just a very simple request, that is, can you sketch the graph of the function y equal to x, where, and hopefully at this level we all know how to do this, right? To sketch the equation of a function, we just make a table like this, and you can choose a bunch of value of x and then find the corresponding value of y, and then draw the point on the xy plane, right, and then connect the points together. You can do this for line, quadratic functions, or in this case, of course, parabola. You can do this for cubic function, exponential functions, trigonometric functions. You can even do this for the case of three-dimensional or two-dimensional functions, right, in three-dimensional space. Of course, it's more complicated that way without the use of computer software. But it's still possible to plot a graph of a function by calculating a bunch of points and then connect the points together if you know the shape. So I want to bring that up so that I want to talk about the direction field and the solution curve that we can obtain from doing similar approach. That is, let's say you have a differential equation of the form dy dx equal to 0.2 x times y. So this first order differential equation. Now what you do is that you have a bunch of points that you're going to consider. So in this case, you have a point -2, 3, -1, -1, 0, -4, 1, 4, and 2, -2. So I'm going to plot this point on the grid here. So -2, 3. So -2, 3, this is one point. -1, -1, this is another point. Right. 0, -4, so this is the point. 1, 4 is this point, and 2, -2 is right here. Okay, so it's just a bunch of points. It doesn't mean anything in the bigger picture at this point. But when you substitute these values of x and y into the differential equation, you will obtain something, and something very interesting, by the way. So dy dx is equal to 0.2 times x times y. So let me quickly do the calculations. So 0.2 times x, which is -2, times y, which is +3. So I don't care about the exact value of the calculation at this point, but what I care is it negative or positive? So from this calculation, I get this is going to be negative. And remember, we substitute the value on the right-hand side, but the left-hand side is dy dx. So the derivative is less than 0. So in a way, y prime is less than 0. Now, the concept of y prime less than 0 or y prime greater than 0 or y prime equal to 0 is back in calculus 1. When you have y prime is less than 0, the function is decreasing. I hope you remember that concept. Right? When y prime is greater than 0, the function is increasing. And y prime equal to 0, you have a horizontal tangent line. So in this scenario, what's happened here with y prime equals y prime is less than 0. So at the point -2, 3, I don't know the exact value of the solution. I don't know how the solutions are going to be, but I know how it behaves at that particular point, right? So the directions on which the solution curve going to behave near this point is going to be decreasing, right? So therefore, you're going to indicate that. Again, I don't know the exact value, right? I just going to know that, just going to see that, okay, the solution is going to behave this way at the point -2, 3, that the solution will be decreased. So that's why I have the small arrow here pointing downward, indicate that this is a decreasing function. Now, again, we do the same similar calculation, but the case of the point -1, -1. So -1, what you got? So zero point 0.2 times -1 times -1, and this y prime is going to be positive. Again, I don't know the exact value of the solution, but I know that near the point -1, the solution is going to increase in that near that particular point. Now for the point 0, -4, going to do the same calculation, 0.2, 0, -4, and because the zero product of 0, so is going to be y prime equal to 0. And therefore, near this point, you have a horizontal change on the line, or just a horizontal line. Okay. At 1, 4, you have 0.2 times 1 times 4. Y prime is positive as well. And 1, 4, this a arrow pointing up indicate that it is going to be in a positive or increasing function. For the point 2, -2, 0.2 times 2 times -2 is going to be negative. So this is negative. So here you have a few points. You plot this few points on the graph, on the coordinate system. And also at each point, you calculate the derivative to indicate that the directions of the solution is going to be. Right? So if y prime less than 0, the solution curve is going to decrease. If the y prime is greater than 0, the solution curve is going to increase. And if y prime is equal to 0, so you have horizontal line at that point. So here, because we only have 5 points, right, it doesn't really show any pattern to the directions of the solution curves. But if you move to the next page, you will see we plot a bunch of points, right, and also the corresponding directions. And let's consider the case of -2, 3, -2, 3, right around here. So you have a arrow pointing down, which is consistent with what we just calculated. Now at the point -1, -1, let's say this is -1, -1, -1 is the arrow pointing up, again, consistent with what we are working on, with what we have. At the point 0, -4, you have the horizontal lines, 0, -4, you have horizontal line as well. So all of this consists with what we just did in this table and graph. Okay, it's just that the picture that you see in here consists of many points, right? You can include more points in this calculation, in this drawing as well if you want to. But with this many points, we in a way kind of see how the solution is going to be, right? So we draw a bunch of curves here to illustrate this is the solution curve, and this is the arrow, all of this arrow combined together to illustrate the direction field, the direction on which the curve is going to behave. Okay, so here in the first picture, you have direction field. And on the right-hand side picture, you have solution curves. If you overlay these two graphs, you will see that the solution curve follow closely with the arrows. Okay, so that's how you obtain direction fields and solution curves. So here, technically, what you can do is that you can draw a solution curve like this. Here's the solution curves, so on and so forth. Okay. So that's how that's what you see here in the solution curves. But as you can see, it's very time consuming, take a lot of time and effort for us to actually draw out all of the arrows and then draw a few solution curves in order to illustrate how the differential or the solution of differential equations behave. I'm not going to do that, right? So this is just an example for you to see how it can be done. At this day and age, usually we just use a computer software for us to visualize the solutions, the direction view, and the solution curves to the first order differential equations. You can use Python, you can use MATLAB, you can use Mathematica to actually do that. But there's no requirement for this course to have Python knowledge or Mathematica knowledge or MATLAB knowledge at all. So that's why I'm just going to use a website. You can access this website, type out the information of the differential equation. Then you can visualize the direction view and solution curves. Okay, and this is going to be one of the questions in the written homework where you interact with the website and then print out the direction view and the solution curves. Now I'm gonna access that website and show you how that can be done. Okay, so give me a few minutes here to set it up. So here's the website that you can use to visualize direction views and solution curves. So the setup is that you're going to plot the differential equations. So don't worry too much about the description here of system of differential equations. What you need to know is that you have a differential equations and you're going to plot this differential equations to, again, visualize direction viewed and solution curve. So this is the setup. The left-hand side is dy dt, and the right-hand side is the function in terms of both t and y, where t is the independent variable and y is the dependent variable. So as of now, the setup of the website is that you have differential equations of the form dy dt equal to sine of t times cosine of y. If you hit plot here, graph face plane, this is what you're going to see. So all of these arrows indicate that this is the direction viewed. And if you click the mouse on any point on this window, you will see the solutions curve. So if I click here, you have the solution curve in red. I click in here, you have another solution curve, so on and so forth. And you can click as many solutions to view as many solutions curve as you like. All right, you can zoom in and out of the window here to visualize a bigger pictures or a smaller picture, or you can zoom in into certain regions to view a particular direction curve, direction view or solution curve. You can increase the number of arrow length. So for example, if I increase the arrow length to 34, you can see it doesn't look as nice as before, or you can reduce the length a little bit here. So this one at this point is just too small to visualize, so on and so forth. You can increase the number of arrows that you want to see in the window. You can increase this to 29, it's too crowded, to sparse for 15, to sparse for 11, something like that. So go back to, let's say the arrow length is 15, and the number of arrows also 15. All right, so the light width, you can increase the light width for the solution curves. It's too big to visualize, this is too small, something like that. Right, so just one for now is bigger, is better. Again, you can change the window of this place. Let's say just zoom into the window between -1 and 1 for the independent variables and -1 and 1 for dependent variable, and then you can grab it again. As you can see, you have a kind of a different point of view into the direction views and solution curves. So that's how you do it. Let me try something a little bit of something else. So to help with the visualizations. So let's do the one in example 2.2 times x times y. But again, the setup of the website is that the independent variable is t, not x. So be careful when you type in the information. So the differential equations in example 2 is dy dx equal to 0.2 times x times y. But in this case, it's going to be 0.2 times t times y. And you click on the graph face plane, and you're going to see this the direction view and solution curve. Right, so click on the screen view point to see the solution curves. Again, you can change the displays or the window of visualizations to have a bigger pictures or better view of the direction view and solution curve. So now I'm going to change to -5 and 5, -5 and 5 here. gonna grab it, and it looks very similar to the two pictures that you see in the notes. Again, to visualize the solution curve, just click anywhere on the screen here to view the solution curves. So let me try one more here, just to give you a good idea of how to type in the information into the website and visualize the solution curves and direction field. So let's do differential equations of the form dy dt equal to t over y. You do this, and then click on graph base plane, and this is the one that you see. So this is direction field, and let's see some solution curve. Okay. So that's it for the website. Again, this is the website that we're going to use to visualize direction view and solution curve, and there will be questions in the homework assignment for you to practice this kind of, entering the information and visualize the direction view and solution curve. All right, so let me go back to the notes.